once I add the blue, it's called closed loop. And very often, even if you have a controller, in order to tune the controller, as we'll see, figuring out what coefficients to put in the controller, we might look at the open loop system, where we take out that, and the closed loop system. And by doing experiments with both, we can figure out how to tune the controller. But we need some words first, some vocabulary. So the first piece of vocabulary is the measured variable or control variable. Well, the control variables, that's the ones we want to control. That's pretty much a tautology. So typically what we want to control, if you're an engineer, is you want to control the profit. Usually control the profit by controlling the concentration of the output or the conversion or the temperature. Those are all things that you want to control. The measured variables, well, one of the measured variables is typically the control variable. So the control variables are part of the measured variables, but you also want to maybe measure other things. So you can measure the control. So for example, if I have 3 CSTRs in series, obviously, well, not obviously, but something I might want to control is the output from the third reactor. But I might not just want to measure that, I might want to measure the output from the first reactor, because if that's going haywire, it's going to affect the output of the third reactor, and I might be able to correct things before things get out of line. So this is an inclusion symbol that the measured variables include the control variables, but they may have other variables as well. So that's the control variables. Then I also have to choose the manipulated variables. And these are the things that I can change in order to influence the control variable. To influence the measured and control variables. And typically, in chemical engineering, the way I change variables, it's usually flow rates. So for example, I could have a flow rate coming in to my reactor system, and then I could have another flow rate that can spike the feed. So I might have a low concentration of A coming in normally, and then if that concentration goes down a little bit, I can have a high concentration waiting in reserve that I could just spike. Or if you like, in the heat transfer system, in the heat exchanger system, I could turn on the flow of fluid from a furnace to another heat exchanger to heat up the system. So typically, I try we like to use valves, pressure control valves. For manipulated variables. Why do we like that? Well, let's say we have a little motor instead of a valve. We had a motor that would pump a pump. If we had a pump, what happens if the pump breaks? Pumps break when they go on and off. Then I got a problem. So imagine I have a nuclear reactor and I need cooling fluid going through the nuclear reactor to make sure that it doesn't melt, like it did in Chernobyl. Well, if I'm relying on a pump and the pump breaks, I get Chernobyl. That is, the cooling fluid doesn't flow, and the thing heats up and it melts and releases lots and lots of radioactivity to the environment. If I'm dealing with a valve, though, and I'm measuring the pressure in the reservoir, when I open a valve, then it will flow. It's just I open the valve, it will flow. And valves are much easier to maintain than pumps, because pumps can just fail suddenly. Valves you can see when they start slowing down, you can fix them. So, plus, you can have pneumatic lines, high pressure lines where you change the pressure and that opens and closes the valve. And they can be a mile long. They don't have to be right next door. So if it's a nuclear reactor and you're sitting in a control room, you don't have to be run down to the reactor and turn a valve. Your control room could be a mile away. What else? Then you have disturbance variables. These can be inputs to your system that you're not controlling. You hope that they're going to be okay, but they could get disturbed, and they can affect your system. So now, and finally, so these are all things that the engineer chooses. You choose. When you're designing a plant, these days, when you design a plant, you design the control system before they build the plant. So that way, when they build it, you have the measuring devices in the places you want them. It's a lot easier to do that before you build the plant than afterwards. And finally, what you choose is the control algorithm. That is, what you want is an algorithm that automatically does the control. You don't want someone sitting there looking at 200 different screens, and when something changes, having to figure out which valve to turn or which pneumatic button to press. Most of the time, you want the reactions to be automatic, and only when something goes terribly wrong should the operator have to do something. But you shouldn't have to do the routine things. So the control algorithm says, when this variable goes up, then open this valve. When that variable goes down, close this valve, etc. So you want that to all be automatic. And so let's see, when you choose, you have to choose these variables. When you choose the manipulated variables, how do you choose them? You look at every control variable. Well, how do I choose them? So when every control variable, I want to make sure that I have at least one, if not more than one, manipulated variable, that if I change the manipulated variable, I have a big effect on the control variable. So, and you have to go through every control variable, you have to have at least one, and preferably more, manipulated variables that will have an effect on the control variable. So, you also want to make sure that you're measuring enough things. You obviously want to measure the control variables, but sometimes you want to measure other things so that you can see what's going wrong before the system blows up. So you need to choose those. What else? Now, how about time scale? What typically happens? You have a process. You have to measure the process. You measure your measured variables. That takes time. Time of measurement. Then there's a controller. There's a time for the controller to react. And then the controller sends a signal. Output signal. That output signal takes time to travel. So that output signal could be an electronic command to change the pressure to open a valve. And then I have the valve. So there's a time scale for the valve to react. And then there's a time scale for the effect of the valve. Change in flow rate. So when I measure something, and I have all these time scales, it's the total times that contributes. That is, I measure something that goes wrong. Until I see an effect, I see tau m plus tau c plus tau output signal plus tau v plus tau effect. So the tau total is equal to the sum of all the tau's. And that's the important tau, is the sum of the tau i's. Because when I measure something wrong, I want to have an effect. And if it takes too long, then I have those delays, which I had up there, e to the minus s theta I. And what we find is that the longer the delays, the less stable the system is. Well, what does that mean? Simple example, you're in the shower. You get into the shower. You say, damn, I have to get to school to hear my control class. So you jump in the shower, and the water's too cold. So you turn the hot water valve, and it's still too cold. What do? You turn it some more. But if there was a long delay, then you've turned it too much. And then when it reacts, the water's going to come too hot. So you start turning it down. It's still too hot. If there's a delay, then you end up turning it too much. So notice, in terms of what we've been doing so far, things are oscillating. And they can oscillate and grow and become unstable. So the bigger your time delays, the harder it is to control. So if I have a bunch of taus and my tau total is too big, I look at the individual taus, and often one of them is bigger than all the others. And I try to make the biggest one shorter. And by the way, that's why we like these pneumatic valves, because they respond really quickly. So now, typically in chemical engineering, the process times are usually long compared with all these others. When we're dealing with a chemical reactor, usually the time scales are hours or days, not milliseconds. In electrical engineering, there's a control class in chemical and mechanical and electrical engineering. In electrical engineering, that's not the case. In electrical engineering, the process, what we call the process times, are just as fast as the measuring times. So they have a much harder problem. And that's why they're the ones who have more than one control class, because it's a harder problem. Occasionally in chemical engineering, particularly if you're dealing with a quickly growing pressure, we can have those situations also. It's just not all the time. There's a little example where they just give you different numbers here, but I don't see any particular reason to repeat those numbers from your textbook. You can just look at them yourself. And when we say a process being fast or slow, if we have a fast process or a slow process, it's always relative to all these other taus. A process is slow if all the taus from measurement to effect, when I add all those taus up, if those numbers are still much slower, much shorter number than the time scale for the process to change, then we call that a slow process. Slow is always relative to something. Fast is when they're the same order of magnitude. If you have a chemical reaction, what is the time scale? If I have a first order reaction, A goes to B, that's mass action, then the rate is kCa. K has units of 1 over time, so the time scale is 1 over K. If I have a second order reaction, kCa squared, then K has units of 1 over concentration times time. Maybe I should write it down. Okay, if I have A goes to product, so I have RA minus KCA. units of K are 1 over time, so the time scale of the reaction is 1 over K. But we saw that the time scale of the CSVR is equal to tau over 1 plus K tau, where this is the space-time. So here, this is the time scale of the reaction, and this is the time scale of the reactor. If I had a second-order reaction, 2A goes to B, Rn minus 2K Ca squared, or K prime. So here the units of K prime are 1 over moles per unit volume times time. And then if I want a time scale of reaction, that's equal to 1 over K prime, but I need to multiply K prime by a concentration, so I might multiply that by Ca steady state, because I need to multiply it by a concentration to get 1 over time. And of course, then I can use this to get the time scale of the reactor. So these are just how I get time scales for a particular system. Are there any questions on that? Okay, and again, I want to emphasize, as we said with the non-interacting system, when I have non-interacting systems, it's the slow mode that dominates at long times. But at short times, the fast modes dominate. When I say the modes, I mean the time scale. So the fast time scales give me my exponential decays quickly, but the system, it never reaches steady state until the longest time scale has already been exceeded. Okay, so I need some more words. The manipulated variable I can't, the disturbed variable is usually something I don't have control over. And I did say already that for each control variable you want at least one manipulated variable, hopefully valve controlled, that has an effect. The manipulated variables have an effect on the control variable, a strong effect that's relatively fast. And you also don't want the change in the manipulated variable to affect everything in the plant. You want it to be localized effect on the control variable. So how do we measure how good feedback control is? Or what are our goals? What are our goals for feedback? Goals for feedback control. So one, we want to minimize the difference between the value of the control variable, this I'm going to call the CD, and the set point. Obviously, we want to minimize that. Another thing we want to do is we want to, and part of that is we want the offset to go to 0 fairly quickly, whatever that means. First, what does offset mean? Offset means, let's say I have a control variable versus time. And so I have some sort of input change. And the control variable is, so here I have an input change. And let's say this is my set point. So I was at the set point, and now I have an input change, and that has an effect. That effect may happen immediately, or it may happen a little bit later, depending on what it is. And now I do my control. So this is the effect of the change in input. Or it could be a disturbance. For example, a disturbance or a disturbance. And now the control reacts. The controller reacts. Sometimes the controller will react and take me to a steady state. That's not the set point. There could be a difference here. And that difference is the offset. So we don't want to have an offset. Now you might say, duh, that's no brainer. We'll see that sometimes controllers that we might think will do a good job actually leave an offset. So we want this offset to go to 0. Another thing we want is we want the rise time to the set point. We want to measure the rise time to the set point to be not too big. What is the rise time? Well, the rise time is, let's say I have the effect of the controller for a rise time. Again, CD versus time. And let's say this is my set point is down here. Set point. It's down here. And I have some sort of disturbance. So things sort of got disturbed. Disturbance is here, and I was going along down there, and now I'm way down here, and another controller comes. And if the controller is mild, then it might come back like this. But if the controller is too aggressive, the controller might overcorrect, and I might go above, and then have to come down, and then come up and down. So this is if the controller is too strong. If the controller overreacts. The rise time is the time between when the controller came on and the first time it crossed the set point. This is called the rise time. So it's the time between when the controller came on and the first time it crossed the set point. It doesn't mean it stayed there. It could have overshot and gone down. Here the rise time is infinite. It never gets there. Here it's finite, but it's maybe too short because I overdo it. And then how do I measure the error? Error measures. So there are a number of ways of measuring error. There isn't an absolute way that's best. So let's let this be epsilon, the error. And epsilon might be a function of time. It's the value minus the second. So there's something called the integral error, which is the integral of epsilon of t to t from 0 to t. So it's integrating error as a function of time. That's not a very good measure. Not very good. Because you can imagine that if the system oscillates and goes above and below the set point, then the positive parts and the negative parts are going to cancel. So it'll look like it's better than it is. So we often use the integral average, the integral absolute error. And that's almost the same thing, but it's epsilon of t prime magnitude dt prime. And so the negative parts don't cancel the positive parts. And there's a final one that I'll end with today, and that's the integral time average absolute error. And that's the integral of 0 to t prime, epsilon of t prime, dt prime. And why is that one useful? So I multiply by t prime. What this does is this penalizes offset. If the offset doesn't go to 0, then this thing just keep growing because the offset is always non-zero. So my controller is going to be based on a measurement of the error. And so it's important which measurement I use so that my controller does a good job. By the way, has everyone signed the attendance sheet? So again, this penalizes offset. This doesn't allow negative errors to cancel positive errors. And this, of course, says at long times you better get back to the second one, and this is going to be big. We're going to continue with this next time. Are there any questions? Next time. So whatever next time is. Okay, so what happens now? Now that this particular class is over, we have a little bit more before we get into the PID. So the next class will be over Zoom. And it will be Wednesday at the normal time using the Zoom address